Writing dissociation reactions in water with monoprotic acids. When we have a monoprotic acid and we look into it in dissociation with water, it's going to separate into its ions. So we're going to have hydrogen as an ion and chlorine as an ion. In the dissociation of a acid with a polyatomic ion. So you want to refresh polyatomic ions and their charges. When you have a monoprotic acid, mono means one, protic, one proton. Then you're going to have that dissociation in water as well with the hydrogen and the NO3. All of this is aqueous. When you have a di or a polyprotic acid, you're going to do this step by step. Step by step. One hydrogen proton, one proton at the time. So HSO4 will first dissociate into HSO4 and then into SO4 or 2 minus. And this is all with water. This is one way of writing dissociation where you're not considering the water as a participant, you're just focusing on the main species and what is happening to it. Let's see with phosphoric acid. The first dissociation, you have H2PO4. And then you're going to have HPO4 until you get PO4, 3 negative. So you could say that there is dissociation 1, dissociation 2, and dissociation 3. When we have a carboxylic acid, we're talking about an organic compound that has the carboxylic group. The carboxylic functional group. And this makes this an acid. You're going to often see for organic compounds where we use R to represent a carbon-hydrogen chain. And this can be any chain that has just carbon and hydrogen. So in here, we need to identify which is the acidic hydrogen. There is several hydrogens here. And the hydrogen that is the acidic hydrogen is going to be connected to the most electronegative atom. And in this case, is going to be our oxygen. So this is the acidic hydrogen. This is the hydrogen that will be donated when this is mixed in water. So the dissociation will look like R, O, and the hydrogen ion. There were a few problems with Arrhenius theory. Not all molecular compounds and substances like NH3 dissolved in water to form basic solutions. So it was like, how can this be when we're expecting OH to be in the formula for our base? It also doesn't explain how some ionic compounds like sodium carbonate and sodium oxide make basic solutions when they're in water. It does not explain why molecule substances like carbon dioxide form acidic solutions, even though they do not contain hydrogen in ions. And it does not explain acid-base reactions that take place outside of aqueous solutions, which also happens. So there is another definition that was determined when it came to acids. And we're going to say that an acid, it's a proton donor. It's any species that donates a hydrogen ion. That's very similar to Arrhenius theory. However, what's different is that a base is a proton acceptor. So any species that accepts a hydrogen ion will be considered. And in order for this to happen, it must have a lone pair of electrons. When we're looking into an acid-base reaction, we're looking into a proton transfer process. So we're going to focus on which of the substances is our proton donor and which of our substances is a proton acceptor. Our proton acceptor must have a lone pair of electrons in their formula. Because we're looking into an equilibrium reaction for these acid-base reactions, we often, in order to understand the forward and reverse reaction, we look into what we have the acid, and we find what form it takes in the product and how the loss of that one proton leads to the formation of a conjugated base. And it's a conjugated base because this form now has a lone pair of electrons to accept hydrogens in the backwards reaction. The base consequently will have this conjugated acid, which in the reverse reaction becomes the proton donor. Your skill is you need to be able to identify acids and base, and you need to be able to identify their conjugated base and their conjugated acid in the backward reaction. So let's talk about that. Identifying and writing Brownsted-Lowey acid bases. So these are all acid dissociations. So one of the two will behave as an acid. Now we're changing where we have water as a participant in the dissociation. And where water is as a participant in the dissociation, we'll see the formation of the hydronium ion and the use of the hydronium ion or the OH. So let's look into that. If I have HF, the form of HF in my products, the only form it can have is where I have fluorine as an ion. Therefore, it means that my hydrogen was donated to the water molecule, so H2O plus. This is the acid dissociation for the hydrofluoric acid. When I look at this carboxylic acid in the presence of water, I'm going to have this C6H5COO. This is going to be my acidic hydrogen, which is donated to the water molecule. So if I were to identify this, I would say this is the acid. I look for its form in the products, and this is the conjugated base. This is the base, and this is its conjugated acid. Acid, base, conjugated base, and the conjugated acid. Remember, just connect what form does this take in the products. Make sure to never miss writing the correct charges for those that dissociation. Right here, this is our acidic acid, acidic hydrogen. So we're gonna have this compound where we have our oxygen by itself, like this, and H2O, H3O plus. This is our acid. And the form that it takes in the products is the conjugated base. This is the base, and the form that it takes, it's the conjugated acid. Perfect. Try this one. Pause the video, resume the video, and then compare. You can do the same for all of these. Try to write the dissociation first, then play the video to continue watching how I do so. So over here, we're looking at the extra step in this sulfuric acid. It has already lost one hydrogen. So to lose the next hydrogen, I'm going to have the SO4 to negative and the H3O plus. This is my acid. This is my base. This is the conjugated acid, conjugated base, and the conjugated acid. Perfect. Base. Brownsted-Lowey conjugated acid base. So over here, we're going to have the NH3, H2O. And we know that here we're looking at the base, how they behave. So NH3 takes on the form of NH4. It has accepted that proton. Why? Because if you look at the Lewis dot structure of this NH3, you will see that it has a lone pair of electrons that can accept a proton. And this is very important. So the 2 electrons will be donated from the nitrogen to attach to that hydrogen that is coming from the water. But it's interesting enough because water then takes on the form of OH. And this is why you see that base behavior. So OH is being released into the solution, but the OH is not coming from the base. The OH is coming from the base, taking a proton from the water molecule. Therefore, our water behaves as the base. The water behaves as the acid because it donates that proton. And the NH3 behaves as the base. This is the conjugated base. And this is the conjugated acid. Here we go. You have fluorine and water. The water is going to donate a hydrogen, forms OH. This is the base, conjugated acid, acid, conjugated base. Same over here. Every time that you see nitrogen, remember, if I were to write this and observe it, I would see lone pairs of electrons in that nitrogen. Therefore, the nitrogen can accept and forms CH3, CH2, NH3. And I have OH being formed. If you struggle to see this, I would suggest to write the Lewis dot structure. So you have CH3, CH2, nitrogen, and it's combined over here, and you have that lone pair of electrons there available. The lone pair of electrons is the one that accepts the proton. This is my acid, the base, it's conjugated acid, and the conjugated base. And finally, with HPO4, I have the water molecule will donate, and I end up forming H2PO4 plus OH. This is my acid, this is my base, and this is the conjugated acid, conjugated base. Now, I want you to pay attention over here. I know that over here we're having this acidic, we're having this base behavior. Because the thing is that the PO4 could dissociate even further and donate that hydrogen to the water molecule. So you will need to be specified what this is doing. Is this in behaving as a base or behaving as an acid? Because it is not as intuitive. Since you have that extra hydrogen in the PO4 form, it can donate it, the hydrogen, or it can accept because it has the protons available to accept, like a base should.